Hello, and welcome to a sort of continuation of Lesson 8.2. Now, this isn't part of our videos for the flipped classroom. This is actually what I'm teaching in class. So this isn't actually part of your homework, but if you were absent, or if you just want to look at it again, maybe a little bit slower, this is what we did in class. In this video, I'm just going to go through two examples of how to graph. And then there's three more examples that you can try on your own, okay? Okay, so a quick summary is here at the top. This just a quick, I tried to summarize all the little information you need to know for this unit, pretty much all the key ideas just right here in this little table. So if you can know all these things, you'll be pretty successful. Now, I'm not going to talk about each one of these things because that's what the previous video was about. The purpose of this video is to practice graphing, and so that's what we're going to do. But of course, we can't actually graph these things unless we analyze their features, so that's also going to be kind of built in and just more practice doing that, okay? So we're still going to follow the same steps and procedures as we've done in the previous video. It's just now we are going to tack on the idea of graphing, okay? So let's start with example 1 here. The first thing I want to start out doing is factoring my function. Putting the function in factored form allows me to identify holes, asymptotes, and things of that nature. The other benefit of putting it in factored form is it'll be a little bit easier to do what's called a sign chart. We've done sign charts before. It's where you make a number line kind of thing. It's not a chart, I guess, but we're going to use the same idea of, signage like this. And so that's what we're going to be doing. Anyway, let's factor this guy. The numerator should factor as, what is that, x minus 3 and x plus 2, I believe. And then the denominator, if we factor that, it should be x minus 3 and x plus 7. Okay, so we've factored this. We identify, hey, I've got a hole here, right? There's a common factor, x minus 3 on top and bottom. That's creating a indeterminate value, 0 over 0. And so that is going to cause a hole in our graph. So we know that the hole will happen at x equals 3. But when we locate a hole, you want to make sure you find the x and y value. So yes, we know that it's 3 comma something. The question is, what is that something? Now to find a hole, just as a reminder, what you can do is if you think of these factors canceling out, then the simplified function would be x plus 2 over x plus 7, right? This is essentially the same function, just it has a hole, where this one has a hole, whereas this one doesn't have a hole. And so we're going to plug in x equals 3 into this function that doesn't have the hole to figure out where that hole is. So let's do that. I want to do x equals 3, so I'll say 3 plus 2 over 3 plus 7, that's 5 over 10, which we know is a half. So my hole is going to be at 3 comma a half. I'm going to go ahead and place that somewhere. Let's say 1, 2, 3, and then a half. So that's going to be, here, I'm going to zoom in and make it nice and boom, look at that. Woo, nice. Okay. All right, now we can, I'm gonna get rid of this, boop, so we can keep looking at our function. Let's look at asymptotes. I know that it says x and y intercept next, but I like to handle the asymptotes next. The vertical asymptote you will find is at x equals -7, because to find vertical asymptotes, you look at when the denominator is 0, except careful for holes. Holes are always gonna kind of overwrite that, okay? So I already have a hole at 3. That means I'm not going to have an asymptote at 3. So I got x equals -7. Let's put a dashed mark make sure when you are drawing this graph, you have to put dashes for asymptotes. Sometimes students are in the habit of drawing solid lines. Don't do that, yeah? Use a dash line. As for the horizontal asymptote, we look at the degrees of the numerator and denominator. I see that the degree on top is 2. The degree on bottom is also 2. So since they have the same degrees, we look at the ratio of leading coefficients. And I can see here that the leading coefficient on the numerator is 1, as is on the denominator. So 1 over 1 is 1, meaning my horizontal asymptote is y equals 1. So now I will draw, as best I can, a little dashed line here, like so. Okay? Now let's find that x and y-intercept, if it exists. To do the x-intercept, you set y equal to 0. Now I'll tell you something. If you set this fella, this guy right here, if you set this function equal to 0, and you multiply by the denominator on both sides, so you multiply it here and you multiply it here, well, 0 times any number is 0. So really, if you just think about what values make the numerator 0, right? Well, x equals 3 would make the numerator 0, and x equals -2 would make the numerator 0. So you might say, okay, I have 2 x-intercepts. Well, no, you have a hole at x equals 3. So be careful of that. We only have one x-intercept, and that is at -2, 0. So I'll plot that. Boop. And then let's see if we can find the y-intercept. Chances are, we're guessing it's going to be somewhere right here, huh? Yeah, so something like that. So let's plug in x equals 0. That's actually, so you could do this in the factored function. I'll let you know, though, if it's expanded, it's usually easier to put 0 here. Because 0 squared minus 0 minus 6, right? I've got -6 on top. Put in 0 on the bottom, you get -21. And so if I simplify that, that should be -2 over -7. That is +2/7. So 0, 2/7. And I'll do my best. We're just kind of sketching, so we'll do our best. That's about as close to 2/7 as I can manage currently. Okay? And so I've got those points. Now, we've labeled all the features, which is mostly what we did in the last video. But notice I have plotted all my features on the graph. Every one of these things, I want to see that on our graphs, okay? I want to make sure you got your asymptotes, you got your intercepts, and if there's any holes, make sure you label them with a nice little hole like so. What will be new now is thinking about where the curve goes. Now, you can pretty easily see that, I'm going to use my laser pointer here, that this curve is probably going to do something like this, right? I mean, it should, because it's going to approach this horizontal asymptote, approach this vertical asymptote. And because it's kind of looks like this, most likely the function is going to look like this over here. Thing is, though, you don't actually know that, do you? Right? Because this doesn't look like 1 over x, right? So it's not necessarily guaranteed that it's going to look like that. It could, and spoiler, it will, but you don't actually know that. It could be possible for me to draw a function like this and then maybe even have something point down like that on the other side. That could happen. So we want to use a sort of sign chart, or I'm just going to use a number line to figure out some of these things. So what I like to do is we're going to make our number line. It's like so. And the key points I'm looking at are asymptotes, vertical asymptotes, and x-intercepts. The thing is, a function, right, if it's doing its la going around, it could, on an x-intercept, it might pass from being negative and then turn positive. So I might want to test a little bit to the left and a little bit to the right of the x-intercept to see whether it's really crossing the x-axis, or sometimes a function will bounce off the x-axis, like so. And in this case, it'd be positive and positive. And so we don't know if it's doing that bouncing nature, if it's passing through it. There are there are ways to know, actually, considering powers, but I haven't taught you that yet, and it's a little bit more prone to pre-cal than Algebra 2. I don't know, so depending on your Algebra 2 teacher. Sometimes you cover it. I don't know. But just so you know, I haven't covered that yet, so let's just go with testing these regions, okay? So look, I've got a vertical asymptote at x equals -7. I also have an x-intercept at -2. Now, what I want to know is the signage in these three regions, okay? That's it. If I can figure out the signage, that should be enough for me to figure out my graph. So, just like we've done before, we've done this with absolute value. What else did we do this with? You doing the quadratics at any point? I don't know. I can't remember. But we've done this before, and you've seen it before, so it's very similar. Pick a little bit to the left of -7, pick something in between, pick something to the right of -2, and just analyze the sign. We don't actually need to do any calculations. So look at your function here. You could ignore the whole, but I'm just going to look at the original to make sure we're really talking about the original. But you can look at the simplified, it's fine. So let's plug in x is -8. If x is -8, now look, I'm not actually going to do any arithmetic here. I'm just going to do signage. -8 minus 3, that is going to be negative. -8 plus 2, that is going to be negative. It looks like a little face, doesn't it? Hee hee hee. Okay, sorry, getting distracted with my own drawing. So -8 minus 3, that's another negative, and then -8 plus 7, oh, that's awful close, that's also negative. Calculating this multiplications, 2 negatives multiplied is positive, same on top and bottom, so the result is positive. So I'm going to come over here and write that this is positive. So the graph of the function will be positive, meaning above the x-axis to the left of -7. All right, now let's test a little bit to the right, say -6. So I'm going to do -6 minus 3. And if I do my sign graph here, so our sign chart, negative, 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 positive. Yeah? So I've just plugged in -6 to every one of these x values here. And that gives me positive on top, negative on bottom, which result is negative. So it's now negative in this region, which means close to the asymptote, because my asymptote's here. Close to the asymptote, that function's going to be negative. It's going to be down here. Obviously, that makes sense given our graph and picture with the asymptotes, but you'll see that you really want to do this sign chart for later examples, okay? Now I have an x-intercept at -2, and the thing is, I already have a point, don't I? Look, I already found the y-intercept, which is to the right of -2. So I've already really tested that, and I know that that's positive. So now let's connect this all together, and I will do my best on my iPad to draw this. I do a little bit better by hand on paper, but I will try my best. Boop. There is this function. It's positive. We know that it's not down here because this would be negative, okay? And then it's going to be negative down here, and then it's got to go through these points. Oops, let's try that. Let's make it a little bit more better curve. Like so. And there's my graph. Okay? And you figure that out. Now, you might ask, Mr. Spake, what points should I be plotting, right? Because in Unit 7, we did radicals. I made you guys plot lots of points on the graph, at least 3 points, right? And not only 3 points, but 3 pretty points, meaning integer coordinates. With rational functions, we're really doing more of a sketch of a function than physically graphing it. Therefore, my expectations for graphing in class on our quizzes, tests, blah, 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 are not as strict about where your points are. The points I care about on your graph are the x and y intercepts. You find those, and it's fine otherwise, okay? You don't need to show me a point over here. What's more important is the end behavior of the graph, how the graph is approaching these asymptotes, and where the curve goes, okay? Because the thing is, we can't get an accurate sketch of this graph without calculus, okay? And I mean like a truly accurate sketch of the graph would kind of require a bit of calculus, because these rational functions, they can do some odd things. I've told you that you can pass a horizontal asymptote, right? You could have a rational function that does something like this. Okay, here, let me try that again. It might go like over and then back, okay? And depending on where you test, right, you could say that it's positive here, but you don't really know whether it humps over the horizontal or if it just approaches the horizontal. I know that maybe that little sketch I did there is a little confusing, but you just don't know, okay? Not unless you find maximum and minimum values, and that requires calculus. So we're not worried about that. Let's just proceed. So let me do one more example. I hope this video is not getting too long, but really that example should be enough. You should be good to go from here, but I'll do one more so you can see it in action, okay? I'm going to factor the top and bottom. I like to pull the negative out. It's not absolutely necessary that you do this, but I'd rather write it as x minus 1 on top and just pull the negative out. And then on bottom, I've got x, what is that, minus 3 and x plus 1? Yeah? Okay. So I have fully factored the function here. By the way, and I did this in class, I would actually prefer that this grid marks, let's make this 1, 2, 3, 4, and 5 on the outside. So I'm going to change. I'm sorry. The graph will look better this way. Just trust me, okay? The graph will look better. I should have chosen smaller grid lines. I apologize. Okay, so let's graph this. So that's 1. I'm sorry. I'm doing this real time. 2, 3, 4, 5. And then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I'm done. I'm sorry. Thank you for your patience. Now, let's plot some stuff. I notice there are no common factors on top and bottom, so there's no holes here, okay? You might say, oh, x minus 1 and x plus 1. No, that's not the same, okay? X minus 1 differs from x plus 1. That is not a hole, okay? Vertical asymptotes, then, I'm going to have 2. Set your denominator equal to 0. It's the zeros of that function. X equals 3 and x equals negative 1. So I'm going to plot those asymptotes. And the reason I extended this grid was just so that we'd have a little bit more space to analyze what's going on in the middle. So this is where our rational functions are going to start looking very different, okay? This one, the one I've done in red up here, more or less looks like the parent function just with a hole. This is going to look bonkers, okay? So let's analyze horizontal. Well, the degree on top is 1 and the degree on bottom is 2. So naturally that means the horizontal asymptote should be y equals 0. This is because the denominator grows faster. One might say it has a higher order, I suppose. Although I don't know if that's the right thing to say. Anyway, the bottom's going to outgrow the top, so it means it's going to get smaller faster, and y is going to approach 0 as you tend towards positive and negative infinity. Okay, and then for x-intercept, well, set the numerator equal to 0, so x is 1, right? Because it's 1 minus 1 equals 0 in the top. There you go. And as for the y-intercept, we plug in 0. What is that? I'll have a positive 1 on top, and then I'll have a negative 3 times 1. So I'll get 0, comma, negative 1/3. So I'll plot those points. Let's do 1, 0, and 0, negative 1/3. Roughly something like that. Okay? And I've got all my features. Oh, I don't have my horizontal. Let me do that. Hello, Mr. Horizontal Asymptote. There it is. Okay? Now, notice, this graph is getting messy. I'm sorry. There's a nice point here, and there's a nice point here. Okay? There we go. Now let's do a little sign chart. As I said, you want to plot your asymptotes, so vertical asymptote at -1, then an x-intercept at 1, and then another asymptote at 3. So we have a few regions to test. So let's test to the left of -1. We could come over here. Let's pick -2. Then this will be negative. We'll keep the negative out here. And sorry, I meant okay, negative on top, and then negative on bottom, and then another negative on bottom. Yeah? And so that's 4 negatives, so that's positive on top, positive on bottom. So to the right, or to the left of -1, it's going to be positive. And that is above the x-axis. So you see, I kind of have two regions I could graph. I could make a curve up here, or I could make a curve down here to the left of that asymptote. Well, it's positive, which means it's going to be in the upper quadrant. So something like that, more or less. You could get a better accurate graph if you really like by plugging in a point and evaluating that point. But right now we're really just sketching, so not a big deal. Notice that to the left of 1, I already have the y-intercept at 0, right? And I can see that clearly right there, that's negative. So I know I already tested 1 here. See, now here's why it's important to test, because I know that the curve will be approaching this asymptote down here and then coming up like so. But the question is, does it come up and then keep going up, or does it travel back down? Because it could do either, and you're not really sure what it is unless you do this sign chart or unless you know your roots and double powers and all that stuff. Okay, so I'll test 1 to the right of 1. Let's try +2. Then I got negative. The top is positive, negative, positive. So that should be positive over positive. Okay, so that's going to be positive. Therefore, it's going to head up here. It's not going down. If it was negative, it would point back down. So I'm going to connect my curve like so through these points. And I just kind of am guessing the shape of that curve, okay? It may not look exactly like that, but what's important is I've got a couple points and the behavior near the asymptotes is correct, okay? Then let's test to the right of 3 because, hey, who knows? Does it look like this or does it look like this? It's going to look like one of those and follow those asymptotes. So let's try 4. I got negative and then a positive on top and then a positive on bottom, positive on bottom. So that should be negative. So it will be down here like so. And then we'll approach this asymptote. Okay? And again, if you want a nice accurate graph, plug in 4 and actually calculate it. You might get a nice point somewhere along this line, and then your graph would be a little bit more accurate than what I have drawn, but that's okay. You've got the general shape of the graph. Now look, let me show you, okay? Does our graph actually look like this? Yeah, 1 minus x. Look, let's do it. 1 minus x over, what was it, x, I'm sorry, we factored it as x plus 1 and x minus 3, is that right? Uh-huh. Look at that. Our graph looks like that, yeah? Woohoo! Boom. I got my x-intercept there, I got my y-intercept, and the end behavior looks good. Yeah, so the general shape we drew was pretty darn accurate. I want to show you something real quick. I wonder if I change this to plus. Ta-da! Look at that. See how this curve, right here I'm tapping it, the bottom curve down there, you see how that curves downward, right? And it also doesn't even get close to the horizontal asymptote. And then, oh no, oh my gosh, over here, there's an x-intercept. It goes below the x-intercept, but then the asymptote is 0, right? So maybe if I threw you this one, your graph might look a little wonky, not 100% correct, but you'd have the end behavior down and you'd be all right. So, okay, that's pretty much it for this video. I hope this was helpful. Here are the practice problems, 1, 2, and 3. I'll probably post a key for this because these are just notes. So there's practice problem 1, practice problem 2, and practice problem 3. I believe 1 and 2 look similar to the practice what we just did, but number 3 is its own interesting graph. So have fun with that. Have fun graphing that. Make sure you identify all those pieces, and there you go. That's the lesson.